Lab 3 is on a black hole, and we're going to be using GlowScript to find the mass of a black hole through using simulations. So first, here are the formulas I'm going to be using. Feel free to pause the video if you want to see the formulas. But pretty much we're just using the force and the change in momentum formulas. So first, with the given code, I'm going to change the seed, change the star mass, and I'm going to set the change in time to 1 day, which is 60 seconds times 60 minutes times 24 hours. And I'm going to put that the change in the momentum equals mass times velocity, and the change in velocity equals final velocity minus initial velocity, and the change in momentum equals final momentum minus initial momentum. And the change in momentum over change in time, that's just delta p over delta t. And then I'm going to also be changing the force net vector to just be equal to dp dt, because that's the only thing acting on the system. Also, the change in momentum over change in time, that's p final minus p initial. And to get the parallel component, I'm going to be multiplying by p hat. And force the net parallel is just dp dt parallel. And then since the two components add up to be equal force the net, that's how I get for force the net perpendicular. And then to calculate the force the net magnitude, I start off with the gravitational force formula, and I solve for the mass, and that's how I get this part down here. And for the arrow positions, the position is just the position which it's following, and the axis is just the force vector. So we can see here that the model runs fine, and it seems like it feels like a greater force when it gets closer to the black hole, which makes a lot of sense. And the average mass, which is an average of all the masses that's given as an output, is 1.02 times 10 to the 34th. So the first what if is, how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So we know F of net in this case is delta P over delta T, and they're pretty much exactly the same, but the only difference is how we calculate the two. For force, we would need to get the force of gravity equation, and for that you would need the mass of the black hole. But since we don't have it, that's why we're using the change in momentum or change in time, which for that we're able to just get the mass from the velocity of the star and the mass of the star. So part 2 is don't crash, so we want to get as close as we can to the black hole and get out of orbit too. So here are the formulas I'm using for this one. I'm just adding in the velocity update formula and the position update formula. So we start with the mass that we got in part 1, and we calculate R for the black hole to planet and black hole to ship, and then we calculate the force of gravity, and then we calculate the force of net. And pretty much it's the same thing for planet and ship, it's just the different R values and different masses. Then with Newton's second law, we're using the position update formula that I said before and the velocity update formula. Same thing for planet and ship, just using the different forces and the masses. And for initial speed, this is what I just ran a few simulations to see which ones would work the best, and this is the initial speed that I found worked the best. So if we look at our model, it gets super close to the black hole, and then it goes out of orbit. So the second what if was, what initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole? So my main idea was just to make the spaceship's speed similar to this planet, since the planet is in orbit. So I set the x speed to 0 and the speed in the y direction to just be half of that of the planet's velocity. Then when I ran the simulation with this new initial speed, we get that the spaceship is orbiting and it never crashes into the black hole or the planet.